This section examines the piston. The piston, with its connecting rod and bearing, transfers the force of the combustion and expansion of the power stroke to the crankshaft. The piston itself, its rings and the piston or gudgeon pin are together called the piston assembly. The cutaway shape on this piston allows it to clear the counterweights on this rotating crankshaft. The shape of the piston crown depends on the shape of its combustion chamber and its compression ratio. The piston crown may be flat, concave, dome or recessed. In diesel engines, the combustion chamber may be formed totally or in part in the piston crown, depending on the method of injection, so they use pistons with different shapes. The piston must stand up to great heat and pressure. It must also change direction from about 10 times a second up to hundreds of times a second. In most engines, the weight of the pistons is important for engine balance. This is why pistons should only be replaced in matched sets. Some pistons are forged, while others are cast aluminium alloys. All pistons expand as they heat up. As there is more metal near the gudgeon pin, this area tends to expand the most. To allow for this, many pistons are machined into a slightly oval shape. This is called cam grinding. Then, as the piston heats up and expands, it becomes round. Other methods to control expansion include steel struts or ribs, expansion slots in the skirt, or slots called heat dams that restrict movement of the heat. This section examines the connecting rod. The connecting rod connects the piston to the crankshaft. It's fastened to the piston at its little end by a piston pin, also known as a gudgeon pin. In some engines, the pin is a press fit in the small end of the connecting rod. In others, it's clamped to the connecting rod with a clamping bolt. Another method lets the pin float in both the piston and connecting rod, and it's held with circlips. There's a bearing in the small end of the connecting rod. The big end of the connecting rod has a detachable cap and carries two halves of the big end bearing. The big end is attached to the crankshaft at the crankpin journal. Connecting rods must be very strong and rigid and as light as possible. They're subject to stretching, compressing and bending, so they're highly stressed. They're cast or forged to form an H near the small end and an I near the big end. This shape provides greater strength to resist the stresses than a solid rod of the same mass. To maintain engine balance, all the connecting rods in an engine are a matched set. This section examines valves. Petrol engines must control the flow of combustible mixture they take in and when it goes in. In small two-stroke petrol engines, this is done by ports that are opened and closed by the piston skirt during the engine cycle, or by pressure-operated reed valves. Diesel engines are different. Their power and speeds are controlled by the amount of fuel injected, so it isn't necessary to control airflow into the intake manifold. Almost all four-stroke petrol and diesel engines use valves, which are located in the cylinder head. This is also true for two-stroke diesel engines that are used in road vehicles. Valves experience enormous stress even in normal conditions. In a four-cylinder car driven at around 90 kilometres per hour, Each valve opens and closes about 30 times a second. Exhaust valves withstand huge temperatures, and they can become red hot. A valve must not soften at high temperatures. It needs good hot strength to stand up to being forced against the seat and to prevent tensile failure in the stem. It needs good fatigue properties to overcome cracking. Various surface treatments are used to help the valve resist wear, burning and corrosion. Inlet valves are made of steels mixed with chromium or silicon to make them more resistant to corrosion, and manganese and nickel to improve their strength. Exhaust valves are made of nickel-based alloys. Some high-performance applications use especially hard-wearing titanium alloys.
This section examines the lubrication system. All moving parts in an engine require lubrication. That is, the application of oil to moving parts to reduce friction between them. A lubrication system distributes oil through the engine. A typical lubrication system consists of an oil sump, an oil pump, and oil galleries. The oil is stored in the sump, bolted to the bottom of the engine block. Oil is drawn from the sump by an oil pump. Oil galleries are small passages in the cylinder block that direct oil to the moving parts. Oil that has been pumped to the crankshaft main bearings travels through oil ways to the connecting rods. Oil may also be splashed from the connecting rods onto the cylinder walls. A filter is usually provided to remove particles of dirt from the oil, and the circulation of the oil assists with the cooling of the internal parts.
This section examines gaskets. Gaskets form a seal by being compressed between stationary parts where liquid or gas could pass. Most gaskets are made to be used only once. They can be made of soft materials such as cork, rubber, paper, asbestos. They can also be made of soft alloys and metals such as brass, copper, aluminium or soft steel sheet metal. Choosing which material and design to use depends on the substance to be sealed, the pressures and temperatures involved, and the materials and mating surfaces to be sealed. Head gaskets seal and contain the pressures of combustion within the engine between the cylinder head and block. They also seal oil passages between block and head, and control the flow of coolant between the block and the head. Some gaskets provide or adjust clearances. Some joints between surfaces on modern engines are being sealed with special sealants which eliminate the use of gaskets in some applications. Gaskets around a rotating part would quickly wear out and leak. To seal these parts, oil seals are needed. Many different kinds have been developed. The most widely used is the lip-type dynamic oil seal. It has a shaped dynamic rubber lip that's held in contact with the shaft to be sealed by a circular coil spring called a garter spring. A similar sealing principle is used to seal the valve stem to prevent oil entering the engine combustion chamber. Rotating or sliding shafts can also be sealed by using O-rings, but generally they're not as durable in most applications as the lip-type seal. As a general rule, oil seals must be replaced when a component is overhauled.